Hello and welcome to Bazant's size effect law by me, Brian Arnold. This is my second time recording this because the first time didn't save, PowerPoint crashed. So for a good one, here's a little disclaimer. This is a project, this is a class assignment prepared for submission to Dr. Rohit Pandey for the Advanced Mind Design class at Virginia Tech this December of 2025. I'm assuming no credibility for any of the scientific findings or research or fractional mechanics or any of the science presented in today's presentation. I've simply compiled this and wrote some words and put it in a slideshow. If you have any questions, please contact me at my email that is highlighted by a box for some reason down there. So this is just a presentation. This might end up on YouTube or somewhere on the internet, so I just wanted to put this out there. I don't own any of this content, and I will put a list of my references at the end. So just for a quick agenda, so we're all on the same page before we dive into this, we're going to go through some introduction, just quickly go over the size effect, who Bazant is. We'll go over the fraction mechanic fundamentals, because I think that's a really important piece of this, and it will aid students in further learning after this presentation, and they can go do homework on their own. We'll go through the size effect, its evolution, how it's changed throughout the years, and some different adaptations of it. We'll go through and see how it applies to geomechanics, because that's the whole point of this class, is advanced mind design, and we talk a lot about geomechanics, so we'll see how this actually gets applied. We'll go over maybe some problems and further areas of research. I'll define some further reading where students can go and check out more sources, and then finally my references at the end. For those that don't know, this is supposed to be a mock lecture for students in a class. We will have pop quizzes and some homework assignments throughout this, so don't worry about those too much. They're just there for what I would say to students if I had them. But feel free to answer the questions on your own. Pause the video. All right, to start off quickly, what is the size effect? Just let's get it out of the way. Well, essentially the size effect is trying to explain why we notice the strength of a structure decreasing as size increases. Now, it's important to note this applies to geometrically similar specimens. So you couldn't go around comparing cylinders to rectangular prisms. We have to be using similar specimens, so a square can be compared to a square. And it applies to quasi-brittle materials, and we'll define that in a second. But essentially, concrete and rock is our main focus point for this whole study today. This is a common misconception to me, because strength should be a material constant in my head. And similarly, you would think that strength would be either constant across sizes, or it might even get stronger as a structure would increase size. It's actually the contrary. From Bazant's size effect study, found that large structures actually are weaker as the size increases. And it's also important to note that the size effect has existed for some time. In fact, folks back in the 1100s were noticing that things that were bigger just weren't quite as strong. And we'll define some of these changes later on in this presentation. But Bazant wasn't the first one to notice that this happens. Bazant was just one of the first to put an equation to it and really focus on the energy component of the fracture happening for quasi-brittle materials. So again, we'll go more in depth in this, but I just wanted to put an image in your head before we get into the fracture mechanics. So essentially, look at this graph on the right. On the left side of this graph, we have smaller sizes. Now, the smaller sizes are trending and following with the strength criterion. whereas structures on the larger side of this plot are following linear elastic fracture mechanics. So Bazant comes in to kind of explain why we're seeing this in quasi-brittle materials, why we're seeing this transition between these two failure modes, we'll call them, and what that area means in between there. And this is becoming a well-accepted thing in the industry. This was originally introduced by Bazant in 1984, but just recently, I think 2019, and we'll get to this in a second, it was adopted into the ACI design codes for concrete. So yeah, it's not just strength. There's also other things going on behind the scenes. So keep that in mind as we go through our fracture mechanic introductions. So really quickly, I think it's important we just touch on who Bazant is real quick. Civil engineer from Prague and current professor at Northwestern Civil Engineering. If you go through the entire list of published works from Bazant and his CV, it's really, really impressive stuff. You'll see a lot of things, a lot of it's involving civil engineering, obviously, but a lot of things focusing on fracture mechanics, creep, shrinkage, and quasi-brittle materials like we're about to study today. If you just try to Google Bazant and size effect, you would think that there'd just be like one paper that has the one answer for everything you need. But the truth is that his work is evolving constantly. Every year there's tens of papers published, and every year I feel like there's something new about size effect. So constantly evolving and adapting, and we'll see that again later. So let's just go over a quick little review of fracture mechanics while we're here. Again, I'm assuming that this class is college leveled and that they have some background, but I just want to touch on this briefly because it'll make things down the road go smoother and aid in further out of the classroom learning. So essentially, why do we have fracture mechanics? That was a big question. Simply put, because materials weren't failing at their strength. We needed something to explain why materials were failing the way they were, and we turned to fracture mechanics. Fracture mechanics help us explain crack energy, the size effect, and various other phenomenon that we can notice in materials is better explained by fracture mechanics. And one thing that you'll see if you dive into this research, essentially, that stress and energy are two different things. And if you compare the stress and crack surface energy, you'll end up with characteristic length. I won't be touching on it today, I don't think, but it is apparent in a lot of these size effect equations. So I encourage on your own to go through and define the characteristic length by yourself. Really quickly, we have three kinds of fracture mechanics. The first being linear elastic fracture mechanics, LEFM. LEFM applies to brittle materials, things like glass. Think of glass. That's probably the best explanation for it. And if we look at the diagram on the right, I think this really puts everything in perspective. We can see the FPZ there, the fracture process zone, and the PZ, the plastic zone, for brittle materials are all very small. Now that's important for LEFM because we're assuming infinite stress at that crack tip. We're assuming that is the zone. That point right there is where everything's going to happen. And we'll see why that's important in a second with our quasi-brittle materials. But essentially, just think about brittle materials there for a second and see how everything happens in that instant. And you can see it with the stress graph right below it too. It just happens in an instant, and that's it. Next up would be ductile fracture mechanics, where we have, again, a very similarly small fracture process zone, but this kind of wide plastic zone where things can deform, and that's where you're seeing ductile behavior happen. If you were to like bend aluminum or something, that's where that would be happening. And we're also going to see Irwin's characteristic length come into play again for that, and it'll play for LEFM as well. But most importantly, we have quasi-brittle fracture mechanics. Kind of the lesser studied area here. We see a lot of stuff with LEFM, not much with quasi-brittle. In fact, we see so much with LEFM, we're about to talk about it next, because LEFM helps us define just about everything that's happening, and it's kind of easiest to put things in terms of LEFM. And we'll see that even Bazant uses it and adopts LEFM to create another version of the size effect down the road. But for our purposes in concrete and rocks, we can understand quasi-brittle fracture mechanics and quasi-brittle materials. Here we see that FPZ now is quite large. It's not concentrated at a single point anymore. There's no sudden stress drop right at that crack tip. And this is kind of the basis for the size effect that Bazant's thinking about, that there's this range of softening, a lot of folks will call it, in the fracture process zone. That's happening at some point around the crack. And the way I would think about it is that there's these little tiny cracks that might be coalescing, or grains interacting, and there's a lot more theories on that we can talk about in a different lecture. But that fracture process zone is really critical, kind of defines quasi-brittle materials for what they are. So again, we talked about LEFM and how it's going to make a pretty big difference in our work here today. So we'll just go ahead and we'll throw some terms out, get some definitions on the board to make our learning a little bit easier. We'll start off simple: stress around the cracks. We just saw a little bit of diagram about how stress is concentrating at the crack tip, and again, that's true for LEFM. In LEFM, that stress will become singular or infinite at the crack tip. Now, this creates some issues down the road when you're assuming infinity at a point, but we work past it, and you'll see this in a second from Griffith and Irwin. Again, Griffith and Irwin do a lot of work in this area, a lot of historic work that comes into play, and they essentially like to relate this flaw length or crack length and the stress at which that fracture will propagate. And they were kind of one of the original ones to relate energy to this equation, but we'll see Bazant takes that energy that we're talking about right now and applies it to the size effect a little bit later on. Again, this isn't a huge part of what we're going to talk about today, but I think that it's important just to kind of preface failure modes here. We have different modes that fractures will occur in. We can see them on the right there. For our purposes today, we're considering mode 1, opening. Now, the reason that fracture mechanics mostly considers mode 1 and that we're going to consider mode 1 is because it's the most common. In general, cracks will start mostly as mode 1, but they can start as mode 2 and 3, and they almost always end in mode 1. Because that mode 1 is the method that we will see cracks actually failing and fracturing and propagating in, we're going to consider mode 1. And we'll see this I or 1 further on in our variables. So I just wanted to preface that now, that everything's in mode 1 or opening. And so essentially we have all of this stress building up at the crack tip, and it's going to be impossible to define what that stress is at the crack tip. So Irwin says, well, let's try to find how fast that stress is tending toward that infinity somewhere near the crack tip. And he coins his term as the stress intensity factor, or K1. So that 1 again is the mode 1 of our cracking, the opening. And similarly, K1 can be written as this nice equation where we take into account stress and crack size as our variables there for our stress intensity factor. So why does the stress intensity factor even matter? Well, because we can bring in fracture toughness. So at what point will a material break? And this is important. This is a pop quiz later, so keep this in mind. Essentially, material can resist this stress up until a certain point, and that's when it'll break, according to LEFM. So we have this mode 1 fracture, mode 1 stress intensity, K1, and when that reaches a certain point, it will break. So that point we call fracture toughness, K1C, C being the point that it'll fail, the ultimate point, and the K1 being the stress intensity in mode 1. And this depends on different things. Material composition, the conditions that you're in, loading rate, orientation, but essentially it depends on the structure and the material. So K1, our stress intensity, will depend on the geometry, the crack size, stress, loading conditions, things like that, whereas fracture toughness is more dependent on the material itself. It will depend on loading rate and orientation and some things like that we have seen in studies, but just to put it in simple terms, it depends on the material. And again, just to define another term here, we just talked about energy. It's important to know that when a crack grows, you're creating new surface area as that crack is opening. And we describe that as an energy per unit area, or surface energy, because it's the area, the energy in the area, surface. Again, Griffith does work in this area and says that a crack will only propagate if there's enough energy in the structure to release and create new surfaces. So this is similar to that stress intensity and the fracture toughness that we saw, where a crack will only propagate if there's enough of a certain thing there. It's stress with stress intensity, it's energy with this crack energy. And we'll see this a lot in terms of G, the energy release rate, and the crack will propagate when it reaches that critical energy release rate, G sub C. And if you dive into Bazant's literature and how they're kind of deriving these equations later on, you'll keep seeing this equation for energy release rate where it involves stress intensity and Young's modulus, where G is equal to stress intensity squared over Young's modulus. And Young's modulus has the apostrophe, the prime on there, to my knowledge, because Young's modulus will change whether you're in plane stress or plane strain conditions. So that's something to note. Again, not really important for us right now. We're not going to go ahead and do any equations related to this, but the moment that you want to go further into the literature and derive some of these equations for yourself and see how they apply, this becomes really important. So important to just throw out there. So just a quick check. This is for the students in the class. Talk amongst yourselves. Real quick one. Shoot it back at me. When will a crack propagate? And I would have accepted 2 answers here, but the main point is when your stress intensity, K1, exceeds your fracture toughness, K1C, the crack will propagate. I would have also accepted when the energy release rate exceeds the critical energy release. So I would also have accepted that, but this is the main takeaway, is that cracks require a certain amount of something to continue, whether that's energy or stress. So we just learned a little bit about LEFM and how this is applying. What about quasi-brittle materials? Because we just talked a little bit about how that fracture process zone was different and how the stress wouldn't build up at the tip, but then we went back on our word and said that it would. Well, that's because we were defining LEFM. Now we're going to transition into our quasi-brittle fracture mechanics. So these are your materials, like concrete. Your quasi-brittle materials are essentially heterogeneous materials with brittle constituents. So think about that in terms of concrete. Concrete is made of brittle constituents, aggregate. Some rocks would be considered brittle. And it's a heterogeneous mixture of different aggregates, cements, different bonds happening in there, hydration products. Just an example of one. And some rocks fall into this category as well. But a very large structure, very large quasi-brittle material will act perfectly brittle. If you were to take a very, very large piece of concrete and you were to load it, you would notice that this would act brittle. It wouldn't act ductile in any way. But the small structures are where we can see that fracture process zone. Having those micro cracks coalesce, and you can notice that fracture process zone do more of its magic. And we'll see some diagrams about this later. But essentially, your most common material for these studies, especially what Bazant was working on, was concrete. And so your failure mode will kind of shift from ductile to brittle, or ductile to brittle over some orders of magnitude. And that essentially is the physical origin for the size effect law. Because we have this fracture process zone, and we notice these quasi-brittle materials will fail differently depending on their size. So I think this graph on the right does a good job of kind of explaining it, where if you would have a ductile material, your stress strain curve would kind of plateau, brittle just drops right off, failure, and quasi-brittle is somewhere in the middle of this ductile, brittle, stress strain curve. And I think it's important to note why we don't have as much good information on quasi-brittle and why it's such an interesting area to study. Again, we've been talking about this fracture process zone. Well, the fracture process zone, you can see from that one diagram, is this region around a crack. It's this zone that's currently uncracked, and it's transmitting stresses away from that crack tip. As you open up the crack more and more, the FEZ will carry less of that stress, and it will propagate and process further away. And essentially, that FPZ is comprised of these micro cracks and these grains that we were talking about, creating these frictional forces that will interlock and push that stress away from the crack tip. And we see that softening behavior in that one diagram earlier, essentially transmitting those forces away from the crack tip. And we can see this in this diagram here to the right, where even at some point before the crack tip, you still notice these stresses around the opening. And again, another little piece of information here, another great diagram. Because we have these micro cracks and grains interacting, there's a lot of different things happening, whether this is bonds and grains failing or that kind of thing happening around the crack tip. I think this diagram on the right again does a great job. We saw the fracture process zone in the last diagram, but here we see it again in kind of a zoomed in version on some concrete here, where you can see those micro cracks existing at a region away, and they get progressively harder to see as you get away from that crack tip because they're encountering less stress, but it's effectively working to dissipate and soften this stress at some point away from the crack tip. So let's tie it all together. We just learned a lot about linear elastic fracture mechanics, quasi-brittle fracture mechanics, and we hinted at a little bit of the size effect. Well, I think that some of the big takeaways here were that cracks in LEFM concentrate stress at the tip, and they fail when stress intensity reaches that fracture toughness. One big takeaway. that LEFM works for these large structures, and we'll see this in Bazant's size effect in his graph as well, that LEFM applies to these large structures because the structure is so much bigger than the fracture process zone or the damage zone at that crack tip. It's almost negligible. So when you encounter a quasi-brittle material with that larger fracture process zone, that's when you notice this important transition between strength criterion and linear elastic fracture mechanics. And that's why we have this noticeable size effect in quasi-brittle materials, because of this larger fracture process zone where stresses are redistributing throughout the material and not concentrating at the crack tip like they would in LEFM. And this is the fundamental thing driving the size effect, right? You have the same material, let's say concrete, you're testing it at different scales, and you're noticing different strengths across those sizes of the structure. And in some regions, they're acting perfectly plateaued across like they would in the strength criterion, and others, they have similar stroke like they would in LEFM. All right, here's some fun time for a class activity. Let's test your basics. So we're going to work with a partner here. You can write this down. You can just shout it out to me, whatever works better. I want you to identify a couple different materials that would behave as brittle, ductile, and quasi-brittle. And I also want you to describe what the FPZ would look like for these different materials. Bonus points if you can throw in the plastic zone in there as well. But yeah, just kind of the main difference between what a brittle material would look like and a quasi-brittle material would look like, and why that FPZ will look different between them. All right, take your time. Ready? Now. Well, some of our quasi-brittle materials would be the cements, ductiles would be more of our metals, and brittle would be glass. I think glass is a perfect example of a brittle material there. And on the right, we can see this fracture process zone in that shaded in area in the top of these diagrams. I'll use my pointer here. Where in quasi-brittle materials, we see this softening, this giant relative to brittle of the fracture process zone. So points if you got that right and noticed how large the FPZ was for quasi-brittle, and I would have accepted quite a few answers here for common materials. But again, just trying to drive home that point of why quasi-brittle is different because of that fracture process zone. So now, after all of this basis that we put into it, we can finally start talking about the size effect, kind of the history of it, how we define it, some equations. In this section, we're not going to go in and derive the equation because we would be here for quite some time if we really wanted to dive into it. And I don't think that it's really important to derive it ourselves at the moment, mostly because this equation is ever changing and there's different approaches to it. And we'll see at the very end there that the size effect has become more well studied, and there's different answers to it. And we'll see that in a second. So don't get too hung up on the specifics here. We really kind of want to understand what's going on from a fracture mechanics perspective, and how this might affect geomechanics. So to start things off, we will, in 1930, I think it was, kind of noticed the size effect and declared it a statistical problem. Some have coined it as the weakest link theory. So it's called statistical because as you increase structure size, you're more likely to encounter, it's more probable that you'll encounter a region of lower strength in your sample, and that's where failure will occur. So In a material like concrete, we can think of this as like the largest critical flaw. So let's say it's an area of a very weakly bonded site of cement and aggregate. And as you increase this material size, that's where that flaw is going to happen. It's going to find it, and that's it. You're more probable to find. It's more statistically probable to happen. And for a long time, this was it. This was the method, and people really agreed on it. And it does explain some things very well. It still does explain brittle materials, and we'll see that Bazant acknowledges it and accepts that it will apply for some types of size effect. So don't count it out. Just know that we might be trying to work against the grain here in a little bit. Mostly because he doesn't include some of the fracture mechanic mechanisms like energy. Doesn't account for those. And again, this has been a notice thing. I just do this slide in here so we can kind of focus on it again, that this is not a new effect. This has been noticed for some time. And Leicester, Australian folk, have noticed this for some time now. And this paper, again, notices that we have a graph on the right here where we're seeing with increased beam depth, we're noticing a decrease in that nominal shear strength. Now, this isn't the curve that we were noticing before, but it's important to know that in 73, they were already proposing different ideas for this and fundamental causes for the size effect, where the first was the material heterogeneity, like the statistical size effect that Weevil had proposed, where you're encountering a flaw. And the other was the occurrence of discontinuities. So I took this to be similar to the size effect, but not because you're more probable, just because they inherently exist in these larger samples. So a little bit confusing of a paper there, but it's important to know that people were thinking about it, having this size effect in their mind, and trying to come up with reasons why this would happen. But again, hasn't yet defined the energy portion of fracture mechanics in this yet. That's what we're trying to build off of. So again, why do we need this? Well, because the quasi-brittle materials were poorly understood. We don't have a sufficient explanation that follows the sample data. Some folks have been able to explain it with the statistical size effect, and some haven't. That's where Bazant comes in, because we still have this looming question of like, what's going on with the FPZ there? What's going on with surface energy? So in 1984, there was this first edition of the size effect proposed by Bazant. A pretty important piece of work. And essentially noticed that fracture is happening around this blunt crack band, or the fracture process zone that I took it to be. And it's not a sharp crack like you would see in linear elastic fracture mechanics or in brittle materials. So this first paper forms two hypotheses, and they're both around fracture energy release. The first being that energy release is a function of fracture length and the cracked area. And that's something that I think we saw with Irwin or Griffith, one of the two, had kind of alluded to this idea earlier, that energy is a function of length and area. And then the second being, again, fracture energy is a function of length and area, just a slightly different form of it. So still going off of this fracture energy formulation from Griffith or Irwin. And what he noticed was from this graph that we saw on the previous slide, I'll flash back to it real quick because I think it's important. Oh, just kidding, I can't go back a slide. But essentially we saw that there was this plateau that's governed by the strength criterion, and then as soon as you translate to larger structures, it starts to follow the linear elastic fracture mechanics route. So here comes this like first equation from Bazant, and there's tons of different forms of it, and it gets referenced in future works as kind of this form that we see on the screen here, where your nominal strength is a function of 1 over the root of your structure size. So one of the things are playing a role in there: tensile strength, some geometric constants happening there. But essentially the important takeaway here is that strength is inversely related to the structure size. So that was the big takeaway. And then this root function gives us this shape that we see in Bazant's size effect. So eventually, I'm not sure at what point in time this came around, but it became more well defined that there were different types of this size effect. So we're going to define a type 1 and a type 2. Type 1, the main point is it's for structures without any pre-existing notches or cracks. We're assuming that failure is happening along a smooth surface when some macro crack forms. It's not related to this buildup of energy at a certain point. So that's why we can come in and say, maybe material randomness does affect the strength. Maybe there is a world where the Weibull theory may explain this. There's like, well, maybe because we're not leaving, we're not putting our own notch in there. Maybe it is running into some problems with statistical reasoning, that maybe it is finding an area of weak strength. And we kind of see that in these larger components. So in future works, and this is from a 2013 paper, we noticed that there's 2 equations we can get from this, one with the Weibull statistical effect and one without it, and just the addition of an extra portion in the equation there. But we'll see that for type 2, we're trying to kind of isolate the ability for statistics to play a role in this. And we really want to know what's happening in that fracture process zone. So we isolate it by adding in a notch and doing 3-point beam bending tests. And that's something important for type 2, which we'll define now. Where type 2 already contains this notch, right? And we can think of it from doing that 3-point beam test where you're breaking something like this with 3 points pushing down. And this is important because we know that in this method, failure will be governed by growth of a crack that we can already see. We already have a length of the crack. We already have an idea of what that fracture process zone might look like. So we eliminate the effects of material randomness on these tests. So this again builds on the idea that stress is accumulating somewhere near the crack tip. And when samples are quite small, they'll behave plastically and linearly along that straight plateau there. And that could be because the sample is so small relative to that fracture process zone that it could have a chance to really affect the strength because structure is so small compared to this already pretty big in quasibrittle materials fracture process zone. So as the structure gets larger, the fracture process zone is then smaller relative to the structure, and then we can behave as an LEFM structure. And we can see here that these equations are quite similar. Linear elastic fracture mechanics kind of assumes that strength is inversely proportional to the root of the structure dimension. And Bazant just kind of adds some tweaks to this to get this curve forming where we can transition from that linear region to that, or from the plastic region to the LEFM region. Yeah, so essentially the big difference between type 1 and type 2, type 1 um, has no existing notch or crack, so material randomness can play a role into it. Type 2, there is an existing crack, so we isolate that, and fracture is completely governed by the crack path and the fracture process zone. So we're kind of isolating it, and we'll see that in further iterations of this equation, we're focusing on this type 2 right here because we're able to isolate the effects of the fracture process zone. It's important to note. And then some future work, 2009, I found this study where they're like, well, what if we introduce both? Because maybe some structures aren't perfectly represented in one region or the other. Some don't have perfectly smooth surfaces, and some don't have an obvious predefined notch or crack. So what about structures with, like, let's say, shallow cracks? Let's provide an equation that kind of transitions. And again, they found a function that relates nominal strength as a function of structure dimension. And it's important to know this area is constantly evolving. Like I said earlier, I feel like from what I've seen in literature, people are just building and building and building on top of this, and the area is getting pretty complex. So take these equations here with a grain of salt, because who knows? They involve a lot of different variables, and the work can change. But I think it's pretty cool here to look at these graphs. They're very similar from just like staring at them standpoint. But let me use my pointer here. Let's just focus on zero crack length. So this would be your type 1 size effect backed up against this wall here. We'll see that kind of follows this statistical curve here, and we see a plateau happen. And we'll talk about that in just a few slides here. But important to notice this plateau is we have no crack length happening. And then when we do introduce a crack length, let's say on this side of the spectrum, that's where we see this drop off with increasing size here that kind of just heads straight towards zero. So that's important, and we'll think about that. But there can exist a region in between your crack lengths where they play a role into the strength too. So it does exist. So again, we've been talking about linear elastic fracture mechanics. So where does this play a role? Well, quasi-brittle materials are difficult because of the fracture process zone and because the energy doesn't concentrate at the tip of the crack like they would for brittle materials. Now, what Bazant came in here and did was define the size effect in terms of linear elastic fracture mechanics. And there's quite a few studies there that have covered this, but essentially now this size effect now also accounts for a shape effect. There's geometric constants in here that define this equation, the size effect equation, based on shape, size, and crack length, because that's what the total energy in the system would be based on, according to linear elastic fracture mechanics. So now we have this equation that we can see here. Again, we have G, the surface energy, E, Young's modulus. In the denominator there, we have these lowercase g equations, and those all have to do, again, with energy release rate. And so literature that I've found back calculates these linear elastic parameters for quasi-brittle materials using this equation. So because we can fit the size effect equation onto test data, we can then go ahead and back calculate these linear elastic parameters that you wouldn't otherwise be able to calculate because it's a quasi-brittle material and the FBZ exists, and so on and so forth. So it makes it easier to determine this fracture energy because this equation exists now. And I'd love to go into the derivation of this, but we don't have time today. These two papers here do a great job of going in and further identifying what each of those functions at the bottom there means, and going and seeing how each piece of the fracture energy release plays a role into this equation. So I highly recommend diving deeper into this at a different time. So where are we at from our current state? What does this look like in the real world? Well, just recently, I talked about it a little bit ago, but 2019, this got accepted for use in design codes by the American Concrete Institute. It's pretty impressive if I do say so myself. There's some more information behind it from Northwestern in the link in the references, but essentially it took a lot of years, but finally it got accepted after numerous databases being published and peers doing more work on it and things like that. Finally got accepted, and now it has to do with beam shear strength. So if you went through this entire lecture thinking that, why do I care about size effect, and it's just something that we're going to use in research and it's not actually real, here we go. It's being used in design codes, and it's well recognized enough to impact the way that we will build concrete structures in America. So, yeah. All right, quick check before we move on. I want you to turn to your partner and explain, assuming you have a classmate, turn to your partner and explain type 1 versus type 2 size effects. If you're at home, pause here. And I showed you that graph earlier where we were combining the type 1 and type 2 size effects in that 3D graph. Think about how that would look in 2D if you had no crack and then a crack, pre-existing crack. All right, take a moment. All right. So, type 1, smooth surface, fails as soon as a macro crack initiates. It could rely on the fracture process zone, could be an energetic fracturing thing happening there, or it could be the statistical side of it. Whereas type 2, pre-existing crack or notch, and it's entirely governed by energetic, and we see this transition from plasticity to LEFM. So again, type 2 is more this focus on the size effect law from Bazant, because we can zone in on that fracture process zone. So on the left here, we can see, I'll get my pointer out, or my laser pointer. Again, this over here would be our type 1, no notch. And notice I was talking about this plateau down here. From the literature I've read, this will plateau to a horizontal asymptote because of the size effect, because at a certain size, or statistical effect, sorry, because at a certain size, the statistical likelihood that you find a flaw, like it is what it is, like you're guaranteed to find it almost at a certain point in size down the road. Whereas with this one, LEFM takes over, and we're still assuming that stress at the crack tip building up, and the statistical component of it won't play a role. So that's where we see this just keep heading down. And we'll see a little bit that this might be a problem down the road, that we're kind of heading straight towards zero, and that it might not apply to some materials. But if you got this part right, congratulations. And if you were guessing these curves look something like this for type 1 and type 2, good job. So to round things out here, let's go over just kind of the applications. Like, well, let's put something real to it. For geomechanics, it's not rare to be concerned about fracture energy and the size effect. In this case, we have a study on Marcellus shale, pretty common test specimen shale here, especially the Marcellus shale. And we can see in the top right here, they have geometrically similar specimens, just like the size effect said they should. And they're noticing a decrease in the nominal strength when they're increasing their structure size, or what they call brittleness number on the bottom there of that graph. But again, we can see the same size effect law proposed by Bazant, where the materials start by following the strength criterion at a smaller size, and they eventually fall into the line of linear elastic fracture mechanics at a larger size. So again, if you went through this entire thing thinking that it didn't apply to rocks and maybe it was just concrete, or maybe it didn't apply to anything at all, here's an example of it applying to geomechanics. This is interesting when you think about it, because how often do we care about the fracturing and the strength of rocks as we get larger? You may think that, like, well, we're not building bridges out of straight rock like we are concrete. Well, it actually makes a big difference, because when you think about test scale specimens, things like laboratory scale specimens are much smaller than what you would encounter in, say, the roof of an underground mine. So if you can properly scale your results according to this effect, you have a better idea of how your strength is going to change as you enter a real situation. I mean, from these results here, if you were to test a small piece of shale in the lab and you were to say, hey, the nominal strength is this, and then you took it to mine scale, well, your nominal strength would have decreased dramatically in that time as you were to scale up. So this is an important area of study. I just wanted to point that out here in this section. And I encourage you, I'll encourage it in a little bit here, to read deeper into the study and take a deeper dive into where we can use this in the real world, because it is pretty important to notice the differences between lab scale and field scale for geomechanics and concrete. So I mentioned this earlier, hinted at it. Is Bazant the only one to notice this size effect? And do we take his equation and his interpretation of fracture energy to be the end-all be-all? And simply put, no. A lot of people have thought about this since then. We can see a graph here on the right. And this is a pretty in-depth study, and again, I recommend you look at this one some more, and there'll be a homework assignment on it, so don't think you're getting away easy. But just take a look at these lines here. So the size effect law, SEL, is the kind of like dot dash line. And for this data set, I mean, the fit isn't great. And then we see the power law from Hoek and Brown. Again, really well studied in the area of geomechanics. We've seen a lot from them. But take a deeper dive into them and take a look at this trend as well. Their trend doesn't fit this data perfectly either. In fact, in my opinion, the best fitting data here would be the multifractal scaling law from Carpentry. And I put this slide in here to kind of reemphasize that this area is still constantly evolving, and materials will behave differently, especially in geomechanics, where you can have the same type of rock and it will behave completely different if it's from 10 feet away in the mine, something like that. We can't just take one equation and one method here as, God. We can't trust that it's going to be the perfect fit, and we can't judge our design specifications completely off of just one fit. So just know that there are more methods out there, and again, homework assignment coming up. So furthermore, the same study is on the right of this one. Well, we just learned that increasing size should equal decreasing strength. That's what the size effect was all about. Well, yeah, some lab results have indicated otherwise. I mean, take a look at the one on the right. We just mentioned that maybe Hoek and Brown might be a little bit better, maybe the multifractal scaling law might be a little bit better, but the data on the right represents a totally inverse relationship. The samples have a higher compressive strength, had larger specimen sizes, structure sizes. So again, this goes against what we've just talked about for the past 40 slides, but rocks are rocks. So I encourage you to dive deeper into this study. It's really important. And again, another study on the left side here where some folks decided that one method wasn't good enough. So they actually combined different models of the size effect to come up with their own universal size effect law, they call it. And maybe that's the best way to do it, is to get a large data set for your specimens at different sizes and fit your own curve and your own data, or combine curves from different methods here. I'm pretty sure the size effect law is the right side of that graph, and then multifractal scaling law is the beginning portion of that. And they just combined those two curves where they met, and just took one size effect type up to one point, and then a different size effect type to another point. So maybe that's the best way to do it. So building on that, here are some reading materials that I think are really important. This first reference here is to a textbook on quasi-brittle fracture mechanics. It is awesome. It is everything you could ever want to know about fracture mechanics: linear elastic, quasi-brittle, the size effect, energetic, statistical. It has everything. It's a full course, and it played the largest role into what I've presented here today. It's pretty in-depth, but if you can make it through it, it is a great help and a great explanation to what the current state of the size effect law looks like for Bazant and other ones as well. It dives into the statistical and some other sources as well. So really helpful. Big thanks to them and that textbook. Again, take a read for the original Bazant size effect law, the 1984 paper. It's evolved a lot since then, but it touches on some great points and kind of contradicts the current assumptions at the time of the statistical size effect. And finally, that one study for the Marcellus shale is the last reference there. Again, really important to take a look and notice how we're taking the size effect into play for current geomechanical research. Pretty important there. And for your homework, there's some homework here. So I want you to go through and find more literature that describes different variations of a size effect or something similar to it, something that explains a change in strength with specimen size, and compare and contrast this with Bazant's. And if you can, if possible, find a paper that mentions using both methods and how their curves have been fitted to their experimental data. And report back on if you think that that's a valid use of the size effect laws, and comment on which variation of the size effect you think fits better. If I had to start somewhere, I would start by Googling multifractal size law, the rock mass size effect, and the classical LEFM size effect. So some great points to start there. I think a quick essay be warranted from this homework assignment and some future reading into these topics. And just to end, here are my references. Thank you to Virginia Tech Libraries and the internet for finding all these. Again, this is where all the information in today's presentation came from. None of it was my personal research or conclusions drawn. So here's the references. Please feel free to dive into any other of these. Thanks.